Hi, Manik. Hey, Manik. We've moved you into the session. Manik, are you ready to start?
Yes.
Okay. So welcome to PyCon 2023, Manik. And of course, to our audience, welcome back. Glad to see you guys. Glad to see everyone back and hope you guys had a good lunch. Do feel free to snack on anything while the sessions go on as well. We're going to be moving into our second session in the data track, which is deploying machine learning models into production. So in most AI-powered projects, teams tend to put a lot of effort into the model training phase in order to obtain a target metric. This talk by Manik Fernando aims to serve as an introduction to the model deployment process after a successful training phase. To introduce Manik to you, he is a senior machine learning engineer at Surge Global, where he is helping to build innovative products that leverage machine learning to solve business problems. Please welcome Manik as he takes the floor with his session, deploying machine learning models into production.
Hey, good afternoon, everyone. Hope you can hear me clearly. Ran into small technical issues a while ago. Can Zara, can you confirm if you can see the screen clearly?
Unfortunately, no. Can you try again? Okay, now we can see.
You can see, right? Nice.
Yes.
Okay. Thank you for the opportunity and thank you for the introduction, Zara. Sorry about the delay again. Today I'm going to talk about getting your model, ML model into production. Let's get started. If time is not with us, I suppose. So, and let's consider the scenario. Why do we need to care about this topic, right? What makes ML deployment different to any other software product that we would be deploying into production? So with AI, when dealing with AI and ML, we inherently, it's a very complex topic and there's a lot of complexity and volatility involved with it. But on top of that, we are dealing with multitude of other aspects apart from code. So we have to deal with data, we have to deal with model artifacts, we have to deal with other binaries and all this stuff. So because of that, keeping track of this, keeping versioning tightly, versioning in line with everything can be a bit of a hassle. Not a bit, quite a bit of effort goes into this. So when we are developing in the initial stages of a model development, if you come from a data science background, you might know this, that we tend to do a bit of a not a very structured approach, one would say. I'm sure there are teams who follow a structured approach, but it's a bit messy because you initially set the objectives, you set the metrics, but once you go into the data, it kind of gets there's a lot of EDA, exploratory data analysis involved. There's a lot of experimentation, a lot of model building involved, and because of this, there isn't a lot of structure in the development that we do at that stage. So what we need to do is we need to kind of get out from this zone into a more robust and more structural approach as soon as possible, and try to kind of streamline our development and hit the target towards the actual deployment. And it is in this day and age, I know machine learning and AI, it's kind of quite popular and there's been a lot of growth. and the barrier to entry has been kind of quite low. But still, there's a lot of things that we need to consider when we go into deployment. So this talk is not going to be like a comprehensive list of things or comprehensive uh, uh, talk that covers everything, but at least I hope this will give you like a basic understanding of things that we can consider in this scenario. So just to look at what the typical machine learning development life cycle is. Again, if you are coming from a data science background, things might be a bit different to this, but generally at a high level, we have uh, at the initiation of the project, what we would do is we define the objectives and the metrics that we want to use to measure those, measure the fulfillment of those objectives. So once we set those through, we'll go into the data gathering and cleaning phase. So in this phase is where you would decide if a certain data set is good enough for you, or if incorporating that data set would hinder your model development, right? And then you would move into this data transformation phase, where which kind of goes hand in hand with the data gathering and cleaning as well. But at the same time, it would this would will be mostly focused on creating a set of data that's consumable by the model training pipelines. So here you will do things like feature engineering, which is basically you look at the data features that's available to you and try to create new features using these features that are already available to kind of improve the model development. Then I think this is the part where you train the model training phase. Here, I suppose in some instances you could do like a hyperparameter tuning instance. So hyperparameters are basically a set of like a configurable parameters of a for a given model. Depending on the parameters you give, the performance might vary. So uh, apart from the actual model training, we kind of need to find an optimal set of hyperparameters as well. So initial stages, you might do a bit of a hyperparameter search, hyperparameter tuning scenario. Then you would move on to model validation. You take that models that you used in the train models and validate on a separate test set, separate set that was not used during the training. And here, what you want to do is, are you hitting this? Are you reaching the objectives that you set by measuring the metrics that you were trying to optimize for? So it might be helpful at this stage to have like a benchmark model or like a baseline model, which basically is like the easiest model that you can build. And what you should strive to do is to perform better than this benchmark or naive model. So this naive model can be something like for instance, if it's a regression kind of problem, you can basically just take the uh, uh, mean value of similar instances, or if it's a forecasting problem, you can do something similar. Or if it's like a classification problem, you can just plainly output the most occurring class as the uh, output. And you'll be surprised in some of these problems, just randomly, not randomly, but just giving the most occurring class might still give you high levels of accuracy as well. So you need to be mindful of those things and kind of decide, okay, accuracy alone might mislead me, but I need to take into consideration other things as precision and responsibility. Then the other aspect would be the main meat of this talk, the main bulk of this talk, which is model deployment, where we want to focus on. And once the model is deployed, we can't really say, okay, my work here is done and kind of brush our hands, because um, models tend to degrade over time, mainly because main reason being that models, the main thing that kind of gives you an output out of a model, at least in the current deep learning and machine learning context, is data. So data tend to not be static, um, and it tend to change over time. So because of these aspects, we need to keep monitoring and kind of see if the metrics that we are looking into kind of go down, we'll have to go back to the drawing board, go back to the model training, or even data transformation, and kind of iterate back into the uh, model and create a new model version. And considering that these kinds of approaches, I think it's kind of in the general deployment, I suppose, use cases, we can make a clear distinction between two types of model inference. Model inference means you take a trained model and make predictions out of it. So there are these types of predictions called batch predictions. Here the idea is you have the opportunity, you don't have to provide the uh, 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 predictions in real time. You can do that uh, ahead of time. You can pre-calculate these predictions, and when the consumer needs them, they will send a query to that, and they can get the predictions out of a store. So one example for this would be, let's say you have a large e-commerce store, and you're forecasting what kind of sales figures you can expect to have in the next month. Since this is a monthly time series and you will be doing this at a daily frequency, you wouldn't need to get like real-time forecasts within the day, right? What you do, what your salesperson might do is every day he or she might come in, they might say, okay, what's the forecast for next week, what's the forecast for the week after that. So the granularity here is not larger than a daily level. So basically, this kind of problem is a nice scenario for a batch prediction, because every day at night you can take that day's new data and look at the past data as well, calculate this forecast, store them in a table, and the next day when during the day uh, the salespeople might come and look at the forecast. Similar example is when you have a recommendation engine. For example, let's say if you visit Netflix frequently, uh, Netflix doesn't have to give you new recommendations every hour, right? So if it can give you recommendations daily, I think that's good enough for them. So they can in this scenario they can each day look at your past viewership behavior, look at the data, and look at similar users and similar shows that you had previously looked at, and make those recommendations and store them. And whenever you visit the site, you will be provided with these recommendations. So the advantage of this approach is you can do large amounts of inferences at once. So you can scale this up to like large, like I suppose in the scale of millions and millions of data samples. Uh, but at the same time, I think it might be a hindrance as well, because you are doing these calculations. If you go back to that Netflix recommendation engine example, you might be making these calculations in vain, because some of these users might not actually come in the next day to look at the recommendations or look for a show. So there's a kind of a sweet spot between giving, deciding on what frequency you want to give the recommendations. And one other nice thing is the consumer or the user doesn't have to wait till the recommendation comes, because it's instantaneously available. You just look at the data store and move on. And usually this kind of ML services are usually triggered by a scheduled job. And uh, and you can see this kind of approaches very usually used in uh, like large scale data platforms such as Kubeflow, Databricks, and even Snowflake as well. Moving on to the other approach, which is the online prediction approach. And here it's a bit more complicated and a bit more involved, and kind of I suppose, the more exciting problem in terms of the whole deployment task. So I think if you can get away with doing batch predictions in real life, I suppose that's the best course of action. Simplicity is always better, but if you must, then you will have to go into this online prediction. So online prediction is where you need to give like real-time predictions, real-time inferences to the user. For instance, you develop an uh, app to identify flowers. The user would take a photo and submit it to your app, and you would identify what kind of flower that is and give the feedback to the user. So you can't really pre-compute this because you don't know what kind of flowers the user is going to take pictures of, right? And what kind of angles and what kind of lighting conditions that the user might use for this instance. So you really can't pre-compute this. So for this kind of applications, you kind of need this real-time inferences and real-time serving of the machine learning predictions. So this is the high level or like a more simplified version of it. That you have a consumer application and it sends a request to the machine learning service, which in this instance is a REST API. And so it's a web service and the machine learning model is kind of embedded in that REST endpoint, right? So, and the request comes to the machine learning, the API would decode the data that the user sent. And depending on the use case, the app can actually request some uh, other data if it's available from a data store as well. For instance, if it's something personal to the user, then you can kind of get that data from a data store or a Redis cache and run the inference. Then you have to send the response. So one of the main things here is that we, like as a consumer or as a user, we really don't like to wait, right? We need things quickly. So getting this with the lowest latency possible is one of the things that machine learning engineers, MLOps engineers kind of try to focus on. And this is suitable for domains that have like very high frequency changes in the data. And this doesn't have to be like online prediction, doesn't have to be purely online prediction. It can, like I said previously, it can take data from a pre-computed data store as well. For instance, let's say if it's something related to, again, language models or something, maybe you can pre-compute some of these embeddings and store them in a data store so that you don't have to do the embedding calculation online. Only you have to do a simple lookup. So that's one example of that. So there are certain drawbacks in this specific approach that I'm showing, is that the machine learning system and the ML REST API are kind of in one entity. So if one of these things fails, the whole system goes down. Kind of a solution for that problem, and which provides other kind of nice properties as well, is this, where we have a model as a service. So you have the consumer application, and consumer application is dealing with directly with the backend API. And backend API is the one that kind of delegates the requests to the machine learning module, which can again be a REST endpoint or it could be a cloud function or something else. So with this way, we are now separating our concerns. Usually machine learning models are kind of known to be resource heavy, and generally web apps are not that resource intensive. So this way we can kind of separate those different types of resources and do a proper resource allocation, because now we can run the web application in a low form factor device, but if need be, the machine learning model can run on like a higher form factor device. It can have a GPU and it can have larger memory, and sometimes you don't really need the machine learning model all the time. Some of the results can be, some of the use cases can be taken care of the uh, uh, web application. And let's say if the machine learning model fails at this point, it's not going to take down the whole cluster. It's not going to take down the node with the web application. Web application now is separate running, and it can identify, okay, the machine learning model has failed. So I can do some kind of mitigation task and give the user some meaningful message, or or tell them to come back later on. And this kind of provides us the opportunity to do horizontal scaling of the machine learning module. Horizontal scaling means you are not increasing the uh, compute power of the uh, machine by increasing, not increasing it by uh, increasing the compute power uh, in individual nodes, but you can add multiple of these machine learning modules. So it doesn't have to be just one, you can have 3 or 4. So this way the backend API needs to have some kind of a load balancing mechanism, which means to kind of delegate these requests to the different uh, machine learning uh, nodes and kind of get the outputs from that. Again, here we have that opportunity to uh, get features out of a data store and use consumers' previous data if needed. So I think again, I needed to kind of come back and kind of make the point that sometimes some of the practices we have in the the initial development phase might not are not very suitable for a deployment scenario. So I think data scientists, myself included, really love Jupyter notebooks, and we love to do all our code in it, and and there are actually lots of services kind of that enabling people to do this in uh, such as NBDev to kind of bring these notebooks into production. But as things stand right now, I think we need to be a bit more wary of the situations where we have, so notebooks are not super flexible when it comes to debugging and version control. If you make a small change in a cell, the version control system might consider that as a change and try to incorporate that into the version control. Uh, there are workarounds around that, and I think there are some nice tools such as VS Code providing the ability to debug inside notebooks. But still, I think we need to be a bit more robust and a bit more back to uh, basics and more principled in our approach when we are going to uh, deploy our models into production. So I think this goes without saying for someone who's coming from a software engineering background, but like if you are coming from a data science background, you might not know about this. Like you can abstract away the main components or things that kind of fit that are common to your uh, code base throughout the application. You can just abstract it away and put it into a package. And only the parts that you can run as a pipeline, maybe you can keep it as a separate Python script and import the relevant modules from the package. And you can actually, like if you once you do that abstraction, I suppose there isn't a lot of harm if you put the pipeline code into a notebook as well. And some platforms such as Databricks, notebooks are kind of the de facto uh, kind of the first class citizen in there. So I suppose in that instance, that does make sense to put the notebooks into a pipeline. But again, we need to be mindful of these abstractions and keep in mind the software engineering best practices to kind of abstract away the main components. So once you have a certain level of structure in your code and you are now ready to kind of getting ready to deploy your model. So in this online prediction scenario, uh, I emphasized the fact that we need to be uh, uh, as low in terms of latency as possible. So, and for that, if you have like a 100 layer neural network, and it's not going to uh, uh, fly well with the consumer, because if they say, if they submit the photo and they have to wait 5 minutes for you to give them the results, that's not going to be a very uh, good user experience. So there are a couple of techniques that I want to kind of bring to your attention here, but these are by no means like a comprehensive list of things that you can do. Um, I mainly focused on things that you can do, I suppose, post training, but some of these things involve training. So pruning is basically, you have, when you have a neural network, you have lots of nodes, not lots of neurons with uh, weights in them, and sometimes, more often, maybe all these weights might not be uh, contributing significantly to the outcome. So basically, what you can do is you can set a certain threshold and look at all the weights that are kind of lower than this threshold, and switch them off, basically bring them down to zero. This way, you are going from a, you can see the diagram on the left, top left, you go from a bit of a dense network to a much sparser network, but at the same time, there's uh, uh, the objective is to make the network smaller, but not to sacrifice performance. So model compression using pruning might have certain um, drawbacks, and to kind of overcome those, another technique called knowledge distillation can be used. So the idea of knowledge distillation is, you use a larger network. Uh, you have a larger network which is very compute heavy, but you wanted to train a smaller network that can give you, that hasn't got a lot of inertia as the larger network. So what you do is, you pass data samples through the pre-trained large network, which is the trainer here, and get the activations, not the final labels, but activations, which are also called logics, right? Let's call them soft labels. Now, the student network, you send the same data through, and we have these pre-computed soft labels corresponding to each object uh, data sample. What we do here is, now for the student network, we have the actual labels. For instance, in this case, the actual label is dog. So we have the actual labels and the soft labels from the teacher network. So we now reformulate the cost function or the loss function as a combination of these soft labels and the hard labels, which are the true labels. So this way, researchers have found that they are able to kind of reduce the network, but like keep the same, like comparable performance in terms of in terms of uh, model accuracy and other metrics. So this is one of the cooler approaches, I think. You can kind of get latency, reduce latency. And one example, I think a well-known example is, if someone wants to further go into this, is called DistillBERT, which is a large language model encoder, and uh, distilled from BERT. BERT is the larger teacher model, and DistillBERT is distilled from that. Another approach is quantization. Basically, what quantization means is, so this, it's kind of, I suppose, as a parallel to pruning as well. So these model weights actually floating point numbers, and sometimes they might have like a high precision. So because of this high precision, these can be quite compute intensive because of floating point arithmetics, right? So because of that, if we were to kind of bring them down into like a integer value, like a 16-bit, or I think in some instances people have used 8-bit. I suppose that those are for like a very crude models. And you instead of floating points, you are basically kind of bringing down the weights and kind of casting them into integers. So this way you can kind of increase the performance. So most of these uh, model compression approaches are kind of available in popular frameworks such as TensorFlow and PyTorch. And just wanted to introduce this other framework called ONNX, which is a open standard, which we'll talk about in a little bit. But the ONNX runtime is another kind of framework which uses ONNX models, and it also provides these optimizations. Right. Another technique is to do batching. So again, just a reminder, we are still doing this online prediction, but here when we do online prediction, so we have the ML system here, and we get like multiple requests, and every time a request comes in, we are sending it through the machine learning model. But these models are kind of built from frameworks such as TensorFlow and PyTorch, and they are very good at doing linear algebra, or basically matrix multiplication and related arithmetic, right? So rather than if you were to send just one vector through the model, and if you were to send this full matrix through the model, the difference between the latency might be very insignificant. So, and especially if you're using a GPU, there's a certain bottleneck where when you are copying the data from the CPU domain into the GPU, there's a certain bottleneck. So in those instances, it might be beneficial to copy as much data as possible to the GPU cores and then move forward. So because of that, it's always beneficial to run a batch of data through a machine learning model than run it vector by vector. So batching in general, what it does is it kind of acts as a buffer, and when requests are coming through, it kind of accumulates this, and at a certain point creates a matrix and sends it through the machine learning model. So this way we can decrease the model latency. Now, so those are some of the optimizations we can do. Now we are going to look at some of the approaches that we can use to actually deploy these models. And I think the easiest, most straightforward would be to kind of wrap your model around a Flask application. But like I said earlier, that might not scale very well. But I suppose with the advent of serverless infrastructure, I think there's a cost-effective approach where you can utilize serverless applications, serverless functions for this. And what you would have to do is define your model inference code within a single function, and kind of use that to infer. So one nice thing about using these functions, whether it be AWS or Google Cloud or Azure functions, I think these have nice integrations with these event-driven triggers, where if you are to, let's say, if you can set up a trigger so that the function will be run when someone uploads a certain file to the to a Google Cloud bucket or an S3 bucket. So we can kind of do this in an event-driven way, or we can actually do this in a using HTTP requests as well. But the kind of downside that I see is that the environment we have is a bit constrained, because getting all the dependencies and, let's say, installing TensorFlow in a cloud function can result in kind of you hitting the memory, the storage constraints. You might need to increase the allowed storage constraints to kind of accommodate installing libraries such as TensorFlow and PyTorch. And then you can't, at the start of the function, you can't really keep the model files like in a persistent storage near the function. You have to keep it in another cloud storage or a blob, and you have to download it at the time when you run the inference. So there's a bit of latency and things involved. of course, if your model is like a small, and if it's not like a deep learning model and it's like a let's say XGBoost model or something, you can totally use a pickle file and load that model into the memory and run this. But though otherwise, those kinds of limitations are there. Then there's the problem of cold start, where you have, when the functions are not utilized for a long time, the underlying infrastructure kind of shuts down, and you have to there's a bit of time for it to kind of get revived again. So there are certain workarounds for this, and it's worth having a look onto what if this is the most feasible thing to do. I think like in the initial stages, when you want to kind of get maybe you have an MVP and you want to get customers feedback, or you want to kind of test something, test a certain hypothesis out, this might be the way to go, and a cheap option. And we can move on to the next approaches, where you have this dedicated inference servers that are built by TensorFlow and TorchServe. TensorFlow serving and TorchServe is available, and NVIDIA has a bit more of a framework agnostic one called NVIDIA Triton. All these frameworks, all these serving frameworks provide you with like an easy way to kind of bundle your model into a Docker container, or it doesn't have to be Docker container. You can run it as a binary as well. But in my opinion, I think this, when I tried out TorchServe, it was a bit involved, because you had to define like a data handler and model. There's another thing called model unroller. So, but I found that TensorFlow serving was a bit more straightforward. You just have to pull the Docker file and run it. And NVIDIA Triton is something you might want to consider for a bit more of a high-end application, where latency is super important and you need to kind of optimize it to the core. And all these options kind of support both REST and gRPC requests. Then there's this ONNX framework, which I briefly brushed up previously. What ONNX does is basically stands as a common platform, because in general, the neural networks are just, if you look at it, just graphs with nodes and edges. So you can it kind of boils down to that at an abstract level. You can take a certain frameworks network and kind of convert it into this open standard called ONNX. And if you want, you can convert it back to another framework. And ONNX supports other optimizations, especially when you are deploying it on an edge device such as a mobile phone. So just want to bring that into your attention as well. But it's not always, I mean, theoretically it works, but it's not always straightforward, because like TensorFlow and PyTorch kind of keeps moving very rapidly and new components keep getting added. So most of the operations, most of the ops might not be at the latest level when it comes to ONNX. Okay, right. Then the other options that I kind of want to bring to your attention was like Kubeflow and Databricks. I feel like although they provide you with similar capabilities in terms of model deployment, I feel like these are drastically different in terms of I would say the learning curve involved. Because like if you take Kubeflow, it's actually a separate open source framework which runs on Kubernetes. Kubernetes is a model, the container orchestration platform. So if you are to do this on premise, you need someone who knows Kubernetes, and you have to deploy a Kubernetes platform. And on top of that, you have to add the Kubeflow framework on top of that. But for Databricks, I suppose the same kind of things apply in terms of the in terms of the complexity, but Databricks is there's a nice managed service with Databricks. Even for Kubeflow, there's a managed service, but I think if you're starting off, if you want to play around, maybe start off with Databricks because it provides you with a like the data lake, machine learning platform, as well as with MLflow, there's a lot of components such as the model registry and model serving. With just a couple of button clicks, you can start serving a model, and you don't have to do any special things. Kubeflow is again nice in terms of that end-to-end machine learning production, where you can train, test, and deploy, run experiments. And Databricks also has those competitive capabilities. I suppose for both of these things, as long as you have the managed services, you should be good. But I don't think if it's something that you're just starting off, you don't need to go for this. But you can kind of iteratively build up to this point from the previous options that I discussed. Okay, I think we are kind of coming to the conclusion here. Just wanted to give a brief note on kind of the machine learning system monitoring as well. So usually software systems can fail due to many different reasons, and machine learning systems, again, I just want to emphasize, are software systems, but on top of that, there are other complexities involved. So because of that, there are a lot of failure. There can be a lot of failure points. So you have machine learning. You have the training pipeline, but the inference pipeline can be different. And if there's no synchronization between these pipelines, in terms of the different data features that you're using, there can be failures, and there can be failures if the data schema changes, right? So one of the main failure cases that we encounter is called this data distribution shift. This happens not because of a code change or a bug change, but because of the underlying data distribution that we train the model in has changed. So one just wanted to kind of point out. So when we train the model, we assume a certain distribution, and although we don't say it out loud, there's an assumption that that distribution would stay the same when we deploy it, right? But in real world, the things are not like that. So there are different types of classifications of data shift, but I suppose the covariate shift is when the input data changes, but the labels kind of stay fixed. But the inverse case is the label shift, where the output or the labels kind of change, but the input data kind of stay the same. And concept drift is when the full conditional distribution or the output of the data changes, but the input side of things stays constant over time. So one I think the easiest example to bring up here is let's say COVID. So like if you had a model that you're using to forecast, again, let's say house prices, which I think some of you might have heard. So if you used a model to forecast house prices, as soon as the COVID pandemic hit, there's going to be a large disruption in the domain, right? And there's a drastic change in the data distribution. Because of this, your previous models are no longer valid. Now, that is an easier problem because COVID happened in an abrupt way. Now you can directly see in your metrics that your model are suddenly not performing well. But the distribution shift can happen over time. It can be very slow moving, and you wouldn't catch it in one go. So because of that, you kind of need to not only look at just one point in time, but you need to kind of look at different points at different time lengths. You need to take windows of different time lengths and take into consideration and calculate your metrics. Like again, when you say calculate your metrics on the data that you have already inferred, for some problems this might not be feasible. For instance, if you have a object detection system and every image your users send you, you can ask them, are you happy with my prediction? But you can't certainly know what the label was for that unless if you go through the process of actually labeling those instances manually. So for in these scenarios, I think the kind of the go-to way to detect drift in your data, drift in your models basically is to kind of look at the input data and kind of see if it's significantly different from the data that you trained on. So this is kind of in the domain of statistics, where you can do like a this test to kind of identify if two data distributions are different, and do a hypothesis test to kind of identify the significance level on that difference. So in conclusion, we need to like take into consideration the complexity involved with machine learning systems. It is important to set up this, set the expectations and the objectives and the metrics at the initialization of the project. But keeping in mind, as we go and as we explore, things might change and we might have to come back to that point and go forward from that. It's always best to start with the simplest approach possible and iteratively increase on top of that. So I think the simplest approach in my mind is the batch prediction. So if you can do batch prediction, totally do that. If you can create a system, a rule-based system than a machine learning system, like using heuristics, first try with that and see how well that fares, and try to beat that with a machine learning system, and try to do batch prediction as a first step. Not all problems kind of goes well with batch prediction. Most problems might need this online prediction approach. So if you come back to that online prediction approach, try with the simplest approach and add complexity layer by layer, and try to make use of these model optimizations to bring down the model compute complexity and reduce the latency. And once you deploy, always keep monitoring your metrics and see if there's a degradation in your model or if there's a degradation in your data. That's it from me. I apologize for the time taken for the delay. Sarah, over to you for that.
Thank you, Manik, for your insights on the different modes of inference, monitoring, and the challenges to keep an eye out for. Thank you to the audience as well for bearing with us and for your patience while we sorted out stuff on the back end. Once again, thanks, Manik. I don't believe that we have any questions that have been dropped in, but I do believe that that was a session that was valuable for everyone. Thank you guys for joining. We'll be moving into our third track now. So we'll see you then.